Today we're going to be talking about the measure or the measures of center when it comes to data. You will want your graphing calculator later on because I'm going to talk about where to find some of these things on your calculator. So if you need to pause it, go ahead and pause the video and go grab your calculator. One of the measures of center that we use, quite frankly, the most is the mean or the average. Statistically, the mean and the average are interchangeable terminology here. I'll talk actually a little bit more about that later. But when we talk about the mean or the average, one of the things that can really throw off the mean is an outlier, a piece of informational data that is much, much different than any of the other pieces of data. And I found this little cartoon here, and this really is a good example of what I'm talking about. These people put together here. The flaw of averages is what they're calling it, which is the idea that if you've got one part that is extremely different than everything else, it can really throw off what the average actually is, or the mean, what the mean actually is. So keep that little cartoon in mind as we go through and talk about this. So our measures of central tendency, I believe you know all three of these, even though I'll be introducing you to some symbols when it comes to this, symbols that you need to know, but are probably new to you. They're the measures of central tendency described where the center of the data lies. The three of them typically are the mean, the median, and the mode. And these are introduced to you way back in 6th, 7th grade, something like that. You've seen these before, where the median is the middle value, the mode is the most common value, and the mean is the center point value. Now that's got a couple of symbols. We've talked that in statistics, a lot of times you want to find out information about a population. And so to do that, you maybe take out a sample and study the sample. Well, then both have their own symbol. They're both referring to the mean. This is the Greek letter mu. This has to do with the population mean. So if you see this one, they're telling you the mean of the population. This is X bar is what you call it, X bar. Kind of a strange name, but that's what it is. X bar gives you the mean of the sample, and you do need to know the differences between these guys. It'll be a couple, 3 chapters down the road, but there'll be times where you're actually going to see both of them within the same formula. And so you need to know the difference between the population mean and the sample mean. Let's take a look at, here's just some data here. Okay, so if I wanted to find the median, well, I would want to probably arrange them from either least to most or most to least, ascending or descending, so that I can sort of pick that out. That's really going to help if you do that, because like here I have it ascending. So we can then start to look through and count, well, where is the middle? I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. I've got 10 pieces of data. Well, wait a minute. 10, the middle isn't exactly one of the numbers. So in those cases, if I had 11, I could then actually just go find the middle. But in the case where you have, so you got the middle is between two of them, and what you do in those cases is you take those two, which happens to be these two right here, you add them up and divide by 2. So the median might not actually be one of the data points. It's the average, and that's what it is the average or the mean of those two. And that would give you the median. Now with an odd number, you're going to have just a number, but if it's an even number, which is why I did it this way, then you're going to take the 2 in the middle. One, they're arranged either least to most or most to least, and you're going to average them to get what it is. The mode is simply the one that just shows up the most often. So you might have to count. This one, you might have to do a little work for, actually. The median's actually sometimes simpler to get. But in this case, it's pretty noticeable. These 3 here just showed up, and so the mode is going to be 9.6. And the mean in this context is the arithmetic mean, which means you just simply add them all up and divide by how many there are. And in this case, ends up being 6.3, which again, notice, is not even one of our data points. And that's the way these things work. Notice that 6.3 is closer to the big end of it than it is to the small end of it. 6.3 would be sitting right in there. And later on when we talk about the normal distribution, we'll talk about how outliers, the farther the outlier is, like the cartoon at the beginning, the farther it is, the more it pulls the mean towards it. The mean is the most susceptible to being moved by outliers. It's more susceptible than the median or the mode. Means and averages. I want to just cover this really quick because typically this comes up in a question. The reason why you hear the term mean and average and people say, well, they're not really the same thing, but yet it's kind of confusing because it seems like you do the exact same thing to get them, is because it's the context that they're being used. If you're talking about numbers, then they're completely interchangeable. What I mean by that is a sum of numbers. When you find the average, you'll find what's referred to as the arithmetic mean. Arithmetic being adding, in which case what you would do is you would add up all the numbers and divide by how many there are. In statistics, when we're talking about the mean, we are also usually talking about the arithmetic mean. So a lot of times in statistics, they're interchangeable, but they aren't truly interchangeable in that there are other kinds of means other than just the arithmetic mean. You probably have heard of this one. I don't think you've probably ever heard of the harmonic. The geometric mean is you take the two numbers, whatever they are, you multiply them together, and you take the square root of that. You saw this back in your geometry class when you found the geometric mean of a right triangle. And I'm not going to go into all that. I'm just saying it might sound a little bit familiar to you from your geometry days. That would have been the introduction to the geometric mean. The harmonic mean you probably have not heard of at this point in time in your mathematical studies. It is a mean that comes up later on. So the point is, the term mean can, no pun intended, mean different things. As long as you're talking about sets of data and some numeric values, the things we're typically doing in statistics, then yes, they can be interchangeable. You really shouldn't run into anything there. The average, though, does not have a symbol, where mean has either the sample mean symbol or the population mean symbol. Okay, moving on. I've already covered this. That's that Greek letter mu, and represents the population mean. X bar represents the sample mean. Summation, hopefully this looks familiar to you. It means you're going to be adding up all the values to find the sum. N, keep this in mind. This is always true. And in the second half of this class, even actually starts before that, we start using these small n's and big N's quite often. Small n is the number of entries in a sample. Capital N is the number of items or entries in a population. Okay, so we've got if it's a sample, if it's a population, if it's a sample, if it's a population. We use different symbols for these. So that's a little confusing because you're kind of talking about the same thing, and at the same time you're kind of not talking about the same thing. It's kind of the context of it. F in statistics will always refer to the frequencies. How often did it occur? Later on, not today, but I've got this here. Here's a context of when we're trying to find a population mean. One of the ways to get that is to take a whole bunch of samples, which, because they're samples, we assume that there's error, and that the sample mean we get is not the actual mean, it's just the sample mean. But the idea will be that if we take enough samples, and then if we average out the samples or find the mean of the means, that is a very, very good approximation of the population mean. So now I will be covering this again another time. I'm just teaching vocabulary right now. I'm showing you that as we go through this, there'll be times when we'll be talking about the sample mean and the population mean in the exact same type of question. So you really need to know the difference between population, sample, sample, population. Which ones are which. Because as you're also going to see formulas, even in your calculator, there'll be situations where it asks you, it wants to know, is this from a sample or is this from a population? because the formulas to calculate them are going to be different in times. All right, outliers. Outliers would be something possibly like this. It's a long ways from the other parts of the data entries that don't fit with the rest, or like this one here, it just really doesn't fit with the rest of them. Much higher and much lower. Now that description there is not the definition. It is a visual description, but it's not the definition of it. To get the actual, is this an outlier? There's actually going to be a formula to calculate that. Is this an outlier? Well, it looks like it visually, but I'd have to use the formula to calculate it. A lot of times, if there are outliers after they've been calculated, many times outliers get thrown out because they do affect the mean by so much. Now, when we talked about mistakes that people make in misleading statistics, and I threw something out there where someone had studied how many scientists, and it was a very large percentage, I do not recall the number off the top of my head, but there was a percentage of scientists who admit to throwing out numbers when they assumed they were outliers, but they never actually took time to calculate. They're just like, well, it seems a long ways away. I think I'll just throw that one out. You got to be careful with that when you're doing research. Research has got to be very structured. If there are gaps or outliers, conclusions drawn might be flawed. And so they, like I said, typically outliers, once they're calculated, then they're going to be thrown out. Like I mentioned already, affecting the measures of center, the one that it affects the most is by far the mean. Whether you're calculating the sample mean or the population mean, that's the one that gets truly affected way more than the mode or the median. Let's go through the mean. Again, when we talk about the mean in statistics, it's the arithmetic mean, the one where you add them all up and divide by how many there are. If it's the population, then you're dividing by the big N, the number of items in the population. If it's a sample, then you're dividing by the small n, the number of items in the sample. And this example here is the idea, if I'm measuring the heights of dogs, or I don't even know if this is heights or weights, then in those cases, you might end up with an outlier, but you would just go through, you get the height of each one of them. It looks like they're doing heights to the shoulder, it seems like here. Add them all up and divide by, in this case, 5. Okay, here's an example. The ages of people in a department are listed. What is the mean age? Add them all up and divide by 1, 2, 3, 4, 5, 6, 7. Divide by 7, and you've got that right there. So that's the mean. I asked you to get your calculators, and here's why. When you get large data sets, it becomes problematic to find the mean by just adding, and then dividing, because the chances of you losing your spot, losing track of which data point you're on, really becomes a real issue. You miss a data point, that's going to very much so change your mean. So kind of a way of doing it, I would say, is if you go to your calculator and hit your stats button and then hit edit. Now there might be numbers in here, which is fine. You just arrow up to the list, hit clear and hit enter, and it'll all go away. Then you can enter in your data. The nice part about this is you can see your data. So when you're looking at your piece of paper with your data written on it, you can keep looking back to see if you missed any. If you're simply just entering it into a calculator, 10.5 plus 13.2 plus 14.9, eventually they get off your screen really quickly after the 4th or 5th number. And then if you miss one, you have a hard time knowing. And I promise you, if you start putting in data that's got 20, 25, 30 data points, at some point you're going to start questioning whether you missed one, especially if you get repetitive ones. I don't see any in this list here, but sometimes you get repetitive ones and then you question yourself, wait a minute, did I already do that? In this case, though, you can just simply look and see if you missed anything. So you put in your data. Then you're going to quit, go second quit, get out of there, and then hit stats again. But this time, instead of edit, you're going to go over to calculate, and you're going to go to single variable stats. You are going to use this a ton in your statistics class. Single variable stats. when you hit enter, it's going to pop up. And actually, if you notice there's an arrow here, this scrolls down. There is so much information here. There's at least 2 full screens of information it's going to spit out at you. And I know that right now, a lot of this doesn't even mean anything to you. First of all, though, you can check. If you have 17 data points and you only enter, and it tells you that this is 16, you'll know you missed one. Or again, this is why this is the preferred way, other than just going this plus this plus this and so on and so forth. Because you'll know how many there are, and you'll know if you missed them. This is going to give you the mean. Now, your calculator will not know at this point if you were entering a population set of data or a sample set of data. But because most of the time in statistics, people are working with samples, it's going to tell you that it's a sample mean. If by chance, though, you were working with the entire population, well, you would just have to, in your mind, say, well, that's my mu, that's my population mean, because the computer is just not that smart. You got to be smarter than the machine. There's other information here that we're going to be going through later on in this course. At this point, we're not going to be doing that. The only other thing that you might recognize is that this means the sum of, so it added up all the values just in case for some reason you wanted it. And the mean, how did it get it? Well, it took this 300.8 divided by this 17, and that's how it got the mean. The rest of this isn't going to mean much to you yet, but it will later on. The median is, this is pronounced x-tittle. It's got this little squiggly thing up there. It's pronounced x-tittle. It's the middle number in a set of data when it's ordered from least to greatest. And technically, I believe it should work from greatest to least, although everybody just does it from least to greatest. If there is no middle number, like the one I showed you before, then you have to average those 2 numbers that are closest to the middle. So example here, you got the price in dollars of some MP3 players, which I know this is an old slide and nobody does this anymore, has MP3 players. We just all play it on our phone, but just go with me on this. Find the median price of the MP3 players. Okay, so here's a bunch of prices. Well, you'd first, of course, want to rearrange them, smallest to biggest, and you can do that if you go through and you hit your sort button. You can do that. So you put these in, and then you find sort on your calculator, and then it'll have it there. You actually don't have to do that, though, with your graphing calculator, even though you can. What you can do with your graphing calculator is you can go through, and right down here, it tells you what the median is. Okay, so if you're doing it by hand, obviously you want to sort it. If you're doing it with the machine, you don't even have to bother. Just put it in single variable stats. It'll tell you what the median is. Unlike the mean, though, the median is referred to as resistant to large swings from outliers. Okay? It doesn't really change that much, even though there might be an outlier. Now, the truth is the median most of the time isn't incredibly useful. What we honestly use it the most for is trying to decide if something is an outlier, and I'll get to that another day. But other than that, we don't actually use the median that often. The mean all of the time. The median sometimes, but not real often. And the mode, quite frankly, we hardly use the mode at all. But we'll cover what it is. Again, it's the one that just shows up the most. If you're looking at a histogram, it's easy. Oh, it's there. Okay. Well, at least maybe I should say in a bar chart, okay? Because this doesn't have classes here. This is just the number 4 shows up the most. Okay, so that's the mode. It shows up the most often. It can be that you don't have any mode at all. If all occur equally, there will be no mode. Or if you have 2 that show up the same amount, you can have, it's called bimodal. You can have bimodal, you can have trimodal, you can have, I don't even know if you call it after that, quadmodal or something like that. Like I said, we don't actually even talk about it that often, and so you probably won't really run into this too much. Once in a great while, we'll have something that's bimodal, and you'll hear me just say it. Oh, this one's bimodal. But for the most part, we don't really see this one. Modes, are they qualitative or quantitative? Well, they can be either one, but usually we're talking qualitative. Now here's another measurement that you haven't heard of. So mean, median, and mode you've heard of. There's another measure of the center here. This is referred to as the mid-range. And the mid-range of data is the measure of center midway, thus the name, midway between the maximum and the minimum. So you simply take the biggest number, add it to the smallest number, and divide by 2. It's always going to be a 2 because you always do this. This is not an average. It's just biggest plus smallest divided by 2. The only time it would ever be the average is when you only have 2 data points. But that's called the mid-range. Biggest plus smallest divided by 2. Here again, this one doesn't show up a lot, but once in a great while we'll end up having to work with the mid-range. So again, with this, well, your first question will be, well, what is the biggest and what is the smallest? The smallest is pretty easy to pick out here. The biggest looks like it's going to be this one. So you'd take those two, you add them together and divide by 2. And this would be called the mid-range. Now the range is how far is it from smallest to biggest. I'm not covering that quite yet. I'm just saying why this would have this name. So if we've got our smallest value here and our biggest value here, midway would be the mid-range. That's what we're doing. We're finding, approximately halfway. The problem here is maybe we get, something in the 15,000s to show up 20 times. Well, by just doing this, it really wouldn't help us then. So it can be a decent approximation for center, but if you have repetitious numbers in one category, then no, it's not a great not a great representation of the center. So, question, would the mid-range be resistant or non-resistant to movement by outliers? Oops, I'll go back. And the answer is this one will be moved. It'll be non-resistant to outliers because an outlier is going to end up either being a really big or a really small number because it's far away from the data. And if it's really big or really small, it's going to pull that mid-range a long way. So if it's really big, it's going to pull it way over here. If it's really small, it's going to pull it way over here. So this one would be non-resistant to movement from outliers. Round-off rule. You're going to run into this. The idea of, well, just how many decimal places out should I go? And the answer is this. When you take a look at your data and these numbers here, we've talked about measuring. Take your measuring with a ruler. You're always rounding a little bit up or a little bit down. We really don't want to get much different than the accuracy you would see from whatever your measurement tool is. So when you've got a situation like this, that's not the one we're going to go from. We're going to round our decimals to one place more than the original set of values. Don't round until your final answer. Okay, so here I've got a total here. If I want to find the mean, well, then I would have to divide by how many are in this data set. Now at this point, if you look at your data, what's the least accurate measurement? Well, any of these numbers, this is obviously a very quote-unquote accurate measurement. These are my least accurate measurements everywhere else. So I look at my least accurate measurements and go one place more than that. Okay, and I should have actually probably put that in here. One place more than the least accurate number in the original data set of values. Okay, so since decimal place is one of these, we just go one more out. Skewness. Okay, there are times when things will be perfectly normal, perfectly symmetric, but a lot of times they're not. Okay, there's going to be values that pull them to the right, pull them to the left. When I say them, I'm talking about the mean, median, and mode. They're going to pull them away. Okay, high values are going to pull the mean farthest away from the center, then the median, then the mode. Notice there's actually a pattern to this. Small values, lots of small values are going to pull the mean to the left of the mode and the median to the left of the mode, which is always going to be the high point. The mode is always the high point. So from the highest point, the mean and the median are going to get pulled right or left. Now, the only time they would all perfectly line up is if it's actually a perfectly normal distribution, completely symmetric left and right, and then all three would be perfectly lined up at the highest point. If it's being pulled to the left, we say it's left skewed or negatively skewed. If it's being pulled to the right, we say it's right skewed or positively skewed. Positive goes this way, negative goes this way. Positive goes this way, negative goes this way. So positive to the right, negative to the left, just like if you were graphing with XY coordinate axes on the x-axis, positives to the right, negatives to the left. Same deal, same kind of thing here. Distributions, I've actually kind of talked about this a little bit before. You can have symmetric, so if you were to draw a vertical line down through the middle, like this one here, and where the mean is approximately the same as the median, which is approximately the same as the mode. I don't even have that here, but this would be considered a nicely symmetric distribution of numbers. Uniform. These kind of are close to a rectangular, quote-unquote rectangular. So like this here. If you were to, take this here, each of the things are showing up about in the same frequency. It doesn't have to be perfect. These are all approximations, okay? But uniform, they're all showing up approximately the same. There's not really like a high and then going down to lows. If you were to take a die and roll the die 10,000 times, keeping track of how many times the 1 shows up, how many times the 2 shows up, how many times the 3 shows up, so on and so forth, you would expect kind of a rectangular looking distribution for the 1, 2, 3, 4, 5, and 6. Different scenario, you take 2 dice, you roll them, and you do a distribution for how many times the sum shows up. Okay, so realize the smallest number you could have then is a 2. 1 plus 1, if the snake eyes showed up, 1 and 1 is 2. Okay, so you could get your 2, and there's only one way that could happen. But think about an addition to get 6. There's actually lots of ways that could happen. You could get a 1 and a 5, or a 2 and a 4, or a 3 and a 3, so on and so forth. So what you would actually find is if you were adding the 2 dice together, it would actually look very similar to this one if you did it a lot. But if you're just rolling 1 die and keeping track, it would probably be more like this. So this is a uniform distribution. This is a symmetric distribution. And this is a skewed distribution. We have skewed left, which is negatively skewed, and skewed right, which is positively skewed. So this one here would be positively skewed. It's more going off in the positive direction. The mean then gets pulled over. It's being pulled. The mean is the most susceptible to outliers. So it gets pulled away from the median, and it's going to go to the right. If the mean is being pulled to the left, it's negatively skewed. Weighted means. Weighted means, this is actually, it's going to look slightly different the way I present this here. But if you recall in another class doing expected value problems, like for, say, a raffle or something like that, or games played at a carnival, this is really the same kind of thing going on here. So the weighted mean, the W represents the weight, which is a percentage. And this is often used to calculate grades. I will tell you that I have your stuff weighted in my class. You've got tests and quizzes. I have weighted more than projects, so on and so forth. And so what does the weighted mean? How do you actually calculate this out? Well, what you're going to do is you're going to take how much it's weighted, that percentage, times the value, and you're going to do that with all the possible values. And you're going to add them up. And then you divide by all the weights. Okay, so let's take a look at an example here. So I got homework, let's say it's weighted at 25%. This is not your class, this is just some numbers here, just throwing this out. Homework's weighted at 25%, and let's say they've got 90 out of 100 points out of their homework. Quizzes are 25% of the grade, and they've also got 90 out of 100. Tests are 40% of the grade, but they've only got 70 out of 100. And attendance is 10% of the grade. And they've been there every day, so they've got 100% out of, or excuse me, 100 out of 100, of course, which is 100%. So the way you would calculate this, you're going to multiply each weight times the value it has. So 0.25 times 90. And then from this one, 0.25 times 90. 0.4 times 70 and 0.1 times 100. And you're going to add all of them together. So you're multiplying the weight times what it's got there each time. And you're going to add these together. And then you're going to divide by the total weight, which in this case is 100%. It's what are we dividing by here? Okay. And this would end up then with a mean of 83%. And this process is how your GPA is calculated. When you go through, you got a 4.0 student, a 3.0 student, a 3.5 student, a 3.3 student, so on and so forth. Those are weighted means. The mean of a frequency distribution, and this is where it actually is going to look pretty much just like those expected value problems. To get the mean of a frequency distribution, you're going to take the frequency, how often does it show up, which is its probability, times the value divided by the sum of the frequencies. So we've got some different ages here, how frequently this showed up. Now in this case, I'm using the class midpoint, so I'm going halfway in between. Now if it wasn't classes, this doesn't have to be in classes. If it was just, a single value, well then you would use that value. But because I've got a class, I'm actually trying to show you a little bit more complicated version of it here. If you do have classes like this, 21 to 30, 31 to 40, so then what you want to do is use your class midpoint, which we covered in a different lecture how to get that. So you find your class midpoints. Okay, so that's going to represent the middles then of this stuff. So you take your frequency times this, and then you're going to add them all up. That's what happened down here. We added all these up. That's my sum down here. And you would take that. I'm not done yet. You got how many words? There's your total frequency. Here's the sum of all of this. Then you would have to divide by the total frequency. Okay, so that's going to be the 76 right there. So then we end up with 35.7. And of course, I would want to round that off. Round off rule here. We could probably go 2 places out, I suppose, because we calculated that. I would argue that ages are, for the most part, if you survey ages of people that are giving you a rounded number to the to an integer, which would make it right here. But if someone wants to argue with me, I suppose I'd take that one as well. Now, in a previous class when we did the expected value, the only difference between how I did this and how I would have done that is I was dividing by the 76 as we went. So each of these would have been a decimal, then I would have just added them up. So it's whether you're dividing as you go here or dividing by the sum 76 at the end, it really is the same thing. It just looks a little bit different as a formula in your book, but that's the mean of a frequency distribution. There we go, roundup rule. I went with the one more than these, but I don't know. I think I'd probably actually go with just one place out normally with this. Okay, let's talk about this. Which one is the most appropriate measure of the center or the central tendency? And we're talking real estate here. So I want you to think about this. Talk about in the region here, in the area, if I want to talk about what's the middle, where's the middle pricing of all of the homes? Do I want to use the mean, the median, the mode, the mid-range? I've got these different tools I could use. And if any of you have looked into real estate at all, you might know that there's one that they always use. You don't ever hear about the average home price, the mean home price. You don't hear that. What you hear about is the median home price. And the reason goes back to, again, that the mean, even though it's very useful in a lot of situations, is very susceptible to being moved by outliers. When you're talking real estate, you got big old mansions out on the lake worth, millions of dollars. And then you got the little tiny, one bedroom thing that's selling for $40,000. Outliers, there's usually not very many of those big things, but they really, really, really distort the mean. So realtors tend to work with the median. It just fits that scenario better. And every type of business, if they're doing statistics, if their business requires statistics, they would have to make that decision for themselves. Which thing makes the most sense to talk about? And the mean really just doesn't make as much sense to talk about as the median. Even though lots of things we go through, the mean is going to be the thing we look at the most often. In research, they're typically talking about the mean. But this is the common sense part of statistics. You have to use common sense. What fits your thing better? All right, there are some problems there to look at. Have a good day.